Benzene represents the baseline of chemical stability. It is a perfectly symmetrical, uniform, and largely unreactive aromatic ideal. Replace a single CH group with nitrogen, oxygen, or sulfur, and that perfect symmetry breaks. The introduction of a heteroatom permanently alters the electron distribution across the ring. This creates the core tension of heterocyclic chemistry. The heteroatom's inherent electronegativity pulls electrons away, fighting against the ring's drive to maintain a stable, uniform aromatic state. The outcome of this structural conflict dictates the molecule's physical fate. It will either become highly reactive or heavily deactivated. To determine which path a specific molecule will take, we have to derive the exact orbital mechanics of the ring, quantify its stability using magnetic shielding data, and track its exact sites of regioselectivity. Mapping a heterocycle's specific subatomic architecture reveals the internal logic governing its behavior, providing the framework needed to predict how it will react in a laboratory setting. For a system to be aromatic, it must adhere to strict physical axioms. It has to be cyclic, planar, fully conjugated, and contain exactly 4n+2 pi electrons. When a heteroatom is introduced, it has to navigate these rules. The geometric path it takes depends entirely on whether it sits in a 6-membered or a 5-membered ring. Examine pyridine's 6-membered ring. Its nitrogen's double bond already contributes 1 pi electron, satisfying the 4n+2 requirement. Therefore, its non-bonding lone pair sits in an sp2 hybridized orbital, sticking straight out in the ring's plane, remaining completely orthogonal to the pi system. Contrast this with pyrroline, where 4 carbon atoms provide only 4 pi electrons. To access aromatic thermodynamic stabilization, the nitrogen rehybridizes. Its lone pair rotates 90 degrees into a perpendicular p orbital, donating 2 pi electrons to complete the continuous pi electron cloud. By integrating into the aromatic sextet, pyrrole's lone pair is trapped. It is no longer available to accept protons, which makes pyrrole an exceptionally weak base when compared to pyridine. The specific hybridization and orientation of a lone pair are determined by the molecule's drive for aromatic stability, effectively defining whether that site will be a basic reactant or a structural anchor. Aromaticity is not a binary state. Stability exists on a measurable spectrum, heavily influenced by the identity of the specific heteroatom in the ring. Within 5-membered rings, 2 opposing forces fight for control. The heteroatom pulls electrons away through its inductive electronegativity, while simultaneously donating them back through resonance. This note documents resonance energies.
Highly electronegative oxytocin in furan hoards its lone pair, resisting delocalization, yielding only 16 kilocalories per mole. Conversely, thiophene's less electronegative sulfur readily shares its lone pair, generating 29 kilocalories per mole of stabilization. This next page explicitly establishes the resulting hierarchy of aromatic stability based on these atomic properties. Thiophene is the most stable, followed by pyrrole and then furan. We can physically measure the strength of these theoretical magnetic fields using a computational method called nucleus-independent chemical shifts, or NICS. By placing a computational probe 1 angstrom above the ring, NICS plots verify the theory. Thiophene produces a dense, continuous magnetic shielding, closely resembling actual benzene, while furan yields a fragmented, highly localized field. Atomic electronegativity directly modulates the strength of the pi electron cloud, creating a predictable and quantifiable hierarchy of physical stability. 5-membered heterocycles are classified as pi-excessive because they pack 6 pi electrons into a tight 5-atom framework. This concentrated electron density causes them to undergo electrophilic substitution much faster than benzene. This reactivity is strictly governed by regioselectivity. When an electrophile attacks these rings, it almost exclusively targets the carbon at position 2. This page diagrams thermodynamic intermediate stability. Attacking C2 yields 3 resonance structures. This extensive delocalization distributes the positive charge, stabilizing the intermediate. Contrastingly, attacking C3 below generates only 2 resonance structures, heavily concentrating the charge into a less favorable route. The rules reverse completely in fused pi-deficient systems like isoquinoline. Here, an orthogonal, highly electronegative sp2 nitrogen alters the entire reactivity profile. This diagram shows the consequence. The nitrogen atom continuously withdraws electron density, deactivating its own pyridine ring. As a result, electrophiles are forced to attack the adjacent, more electron-rich benzene ring, specifically at the 5 and 8 positions. Lone pair geometry determines the overall speed of a reaction, while simultaneously defining the exact atomic coordinates where a chemical attack will occur. In the laboratory, chemists exploit the thermodynamic energy drop of achieving aromaticity to force straight-chain molecules to cyclize into complex heterocycles. This flowchart outlines the Bischler-Napieralski reaction, a method for synthesizing isoquinoline starting from beta-phenylethylamine precursors. The critical step requires a dehydrating agent, phosphorus pentoxide. By removing water, it physically drives the ring closure, stepping the intermediate towards its final locked aromatic state. For systems combining a benzene ring fused to a pyrrole, we look to this historical document detailing the Fischer-Indol synthesis. It remains the primary method for creating the indole core. Heating an aryl hydrazone with an acid catalyst initiates a cascading 3,3 sigma-tropic rearrangement. The molecular framework physically breaks and reorganizes its sigma bonds. The irreversible step is the elimination of an ammonia molecule. This ejection provides the ultimate thermodynamic drive, snapping the newly formed pyrrole ring permanently shut. Laboratory preparation is an exercise in designing chemical pathways, where the final step drops the molecule into an inescapable aromatic energy well. A molecule's high-level chemical behavior is a direct output of its subatomic orbital architecture. The specific orientation of a heteroatom's lone pair, sitting orthogonal to the plane or perpendicular to it, establishes the molecule's baseline aromatic nature. The atomic electronegativity of that heteroatom then dictates how tightly electrons are held, determining the ring's precise ranking on the aromatic stability spectrum. That exact stability profile maps perfectly to its reactive regioselectivity and dictates the condensation methods required to build it from scratch. In physical organic chemistry, structural formulas represent strict geometric laws that govern all future thermodynamic behavior.